Okay, so I'm Martijn Vermeer. I work for Science and Technology, and we are a small company based in Oslo. And normally we mostly work with satellite imagery analysis. So the previous talk was quite interesting for us. But today I talk about CryoSat-2 waveform classification for melt detection. And CryoSat-2 is a radar altimeter. So here's the presentation outline. I'll dive straight into it. So first I'll introduce the project EO for SMB, which is a larger project funded by the European Space Agency. And this study is part of this larger project. So today we'll only talk about a subpart of this larger project. So the goal of this larger EO for SMB project is to measure the surface mass balance of the Greenland ice sheet using Earth observation data. So let me just make that small. Yeah, so the surface mass balance, I put a definition below on the slide, is the net mass balance of accumulation and ablation processes operating on the surface of the ice sheet. So these are all the processes like precipitation, raining, snowing, melting, refreezing, runoff that contribute together to this surface mass balance of the ice sheet. And the surface mass balance in turn is part of the total mass balance of the ice sheet. And the total mass balance is very important when it comes to, for example, climate modeling. But today we'll just focus on one of these parameters, surface melt. So the issue is that currently there's no complete record of surface melt available for the Greenland ice sheet. And this is due to different sensors having different issues, but I can give some examples. Spectroradiometers, they're impacted by clouds. So when it's cloudy weather, there are no measurements. And then there's other instruments, but they have issues with incomplete or irregular service at the ice sheet scale or limited spatial and temporal resolution. And the idea here is that CryoSat provides monthly measurements over the ice sheet. So it has a monthly revisit time. And it gives therefore quite a continuous record, and therefore it has the potential of making this record of melt more complete if we manage, and that's then the goal of this study, to classify CryoSat-2 waveforms using machine learning in order to detect melt. So on the right, we see a schematic image where we have a CryoSat-2 satellite in orbit. It sends down a radar beam. This radar beam has a footprint of 250 meters on the surface. Then it's important to realize that this radar beam, it penetrates the snowpack to a certain extent. And then the reflection of this radar pulse is measured. And this gives the waveform shown in the image. So we see a very strong leading edge, which is the surface reflection, and then a degrading signal with depth. And normally radar altimeters are used to measure the elevation of the surface, but we are in this study only interested in the shape of the waveform, as this shape of the waveform holds information on the presence of liquid water. So by classifying this waveform shape, we are hoping to detect melt. So a bit more on the two satellites we're using. So I already mentioned this CryoSat-2, which is an ESA satellite. It's a radar altimeter. It has a monthly revisit time, and it takes these beam measurements of 250 by 250 meters. But then as reference data, so in order to label these waveforms as melt or no melt, we're using MODIS data, which is a NASA satellite. It's a spectroradiometer, so it's impacted by clouds, and cloudy weather, there are no measurements. It has a daily revisit time, and it acquires an image grid with pixels of 1 by 1 kilometer. So our research area and period, the research area is the Greenland ice sheet. We're focusing on the interior part, depicted in red here. And our study period is starting in 2011, since this is when CryoSat-2 became operational. Yeah, then a bit on data preparation. So how do we construct this data sets for machine learning? So we have all our CryoSat-2 waveforms, which are these point measurements. So on the right image, these are these black lines. There's a lot of points along these orbit lines, but we need to label them as melt or no melt. And for this, we use this MODIS data. So on the image, the MODIS data is the red and blue image, which is then showing the lens surface temperature. So what we do for each CryoSat-2 measurement, we find the corresponding MODIS measurement of the same day, and we link the two such that we can, and then we simply threshold the temperature at -2. If it's above that, we label it as potential melt, and below as no melt. So this -2 may sound a little bit weird, but you should take into account that these MODIS pixels are 1 by 1 kilometer. So it can quickly average out to be -1 or -2, even though there is melt present in this larger pixel. So this is why we choose this threshold slightly below the freezing point. And then not all these waveforms can be matched, and that is due to the fact that we have these clouds or poor quality MODIS measurements in some instances. So the result of this is a highly imbalanced data set with only 5% of the waveforms labeled as melt and about 95 as no melt. And this imbalance is also varying over time. So you can imagine July is the warmest month. Then of course we would have more melt than in June and August, for example. Yeah, then on the data split, so we split this data set in a train, a validation, and a test set. We're keeping 2012 and 2017 separate for validation for tuning hyperparameters, and 2020, which is completely outside of this period, for testing. And then we selected a number of evaluation metrics, and these were mainly selected because they handle in some way the class imbalance, or they are robust metrics having a high class imbalance. So then, before we go to this deep learning approach, we decided to make an ML baseline. And the reasoning here is that this topic, there's no previous literature on the classification of CryoSat-2 waveforms. So we wanted to have, at least this classical ML baseline to compare our DL approach with, in order to see, okay, is there any added value in DL in this case? So we extracted common waveform features and used the AutoML Teapot tool to find a robust classical ML solution. So here in the image, we just see some of these features, the histogram for some of these features, but this is a long list of features that was used in this AutoML solution. Then the proposed deep learning approach. So the architecture was mainly selected with two things in mind. We wanted to have a simple architecture, as this study is more of a proof of concept rather than getting the best possible results. And we wanted to avoid overfit, because we know we have a limited data set, and especially with this class imbalance, we only have a limited amount of samples on melt. So we started with a VGG-like 1D CNN architecture that has an encoder with 5 convolutional blocks and a classification tail with some fully connected linear layers. And then the architecture that I show here is with these exact number of kernels that was found by means of a hyperparameter search. So we searched through different varieties of this 1D VGG-like CNN. Then we use so the input is this 128 vector waveform, and the output is then, after the sigmoid, a prediction of 0 to 1 melt/no melt. And then finally, we apply some augmentation by shifting the waveform along the x-axis. So like I was saying before, we are not interested in getting the elevation from the waveform. We're only interested in the shape. And that's why we can safely shift this waveform somewhat back and forth to artificially create more data. Yeah, so this gives us the following results for the TPOT baseline and the DL approach. So for the DL approach, 80% of the no melt waveforms is predicted correctly, and 75% of the melt waveforms are predicted correctly. And here it's very important to take into account that I'm listing this as melt, no melt here, but this labeled data is this thresholded land surface temperature data from MODIS. And that is, of course, there's not a one-on-one relationship between the surface temperature and melt or liquid water being present in the snowpack. So our true data, our reference data, we know that we have some error in our reference data. So that is important to keep in mind. Then we know that in 2012, there was very extreme melting occurring on Greenland, especially in July. So we processed the June and July months for 2012 in order to see if we can capture or if we can see back this event in our data. So the left two images here are the raw predictions, where we see that in June, we have in red some melt towards the boundaries of the ice sheet, and in July, it's extending farther land inwards. And this test of processing the same area for 2 different time periods is also showing us that it's not completely overfitting, at least on location. And then on the right side, we have the 2 corresponding land surface temperature maps from MODIS. And then we can look into more detail for a specific location. So what we did is we looked at the summit station on Greenland, which is on the top of the ice sheets. And for this station, there is a temperature record available. So the red line in the top graph gives the temperature for the summit station during the 2012 summer season. And we have now processed all the available CryoSat-2 measurements within a 50-kilometer radius of this summit station and made a time series of melt in this region. And the idea was here that we could then compare whether this melt that we're detecting or predicting with our model is lining up with the temperature record that we're having for this location. So there we see indeed that on the 12th of July, where temperature exceeds 0 degrees for the first time at this location, we are seeing a peak in the melt prediction. And similarly, when there's close to 0 temperature values in late July and early August, we're also having high prediction values. Yeah, so to conclude, the main limitation of the current approach is that we don't have actual in situ reference data, such that the MODIS lens surface temperature does not correspond in reality one-on-one with melt. So we're thinking about solutions here, and one of the things that could potentially help is look at a time series of land surface temperature for a certain location. So look at how has the temperature been the last couple of weeks, and based on that judge whether we expect liquid water to be present in the snowpack. And in that way, construct a better training data set. Then we could also look into alternative deep learning approaches. So investigate sequence modeling, RNNs or transformers, look more into data augmentation, additional data sources, or reformulating the problem as a regression task. But finally, the conclusion is that we hope we've shown with this study that it is feasible to detect melt by classifying CryoSat-2 waveforms using machine learning and deep learning. That was my presentation. Thanks for the attention, and yeah, let me know if there's any questions, or any suggestions are also welcome, because this is still an ongoing project.